It's an interesting sign of the times that in the deep learning session next door, the room is packed, standing room only. It's about, only about half full in here. But rest assured, the work that all of you do continues to be very important. And I think that there are a lot of things that the deep learning world can learn from high-performance computing. And in fact, Steve Parker showed this slide in the keynote. And he talked about how important computational science was to NVIDIA and to the work that we do. And that certainly remains true. But as it turns out, data science, all of that AI work, all of that deep learning work, is actually not very useful without high-performance computing. And again, I'll show you some numbers. The concept of a deep neural network was written about in research papers 30 or 40 years ago. And the challenge was it simply wasn't effective to do research using a deep neural network. The results were not good enough. And the reason the results weren't good enough were really twofold. One, the availability of data. Like 30 or 40 years ago, no one had a lot of data. The second thing was the time that it took. Even today, to train an average, on an average data set, a deep neural network, using a CPU-only system, can take about 30 days. Now, that may sound really bad. I need to wait 30 days to get my results. But it's actually much worse. To train a deep neural network, to get good results, you often have to train your deep neural network 40, 50, 100 times. And so if you're a PhD researcher, even a PhD researcher, and you tell your advisor, well, I have this idea, but it's going to take me 100 months to get any results, your advisor will ask you to take another approach. And that's exactly why deep learning never took off. Until about 4 or 5 years ago, when some of the first researchers said, well, let me take this deep neural network algorithm and actually run it on a GPU. Maybe it'll be fast enough to get some interesting results. So what we're seeing today is that all of the large consumer web companies and others that are implementing deep learning are doing so using HPC technologies. And we'll show you some examples. And HPC sites are all looking at deep learning as a new way to solve problems that they haven't been able to solve before. And in fact, we believe that large HPC systems at the university level, at a national lab level, at a corporate level, won't be built anymore only to do computational science. That every new supercomputer built will have to be affordable, to have interesting results, will have to be used for data science as well. And we don't believe that, at least in the near future, people will build large systems for data science without using HPC technologies. So what's so different about deep learning in data science, and how does that fit in? Well, again, in case you're not familiar with it, you really have your traditional data pipeline. Where's the data created? HPC centers are creating huge amounts of data every day, either from measuring sensor data, satellite data, a camera, the Large Hadron Collider is maybe the ultimate example, but real-world data that you're measuring, or using computational science, you're running a simulation, and you're creating that data. And again, not that people won't write if-then-else code anymore to process that data, but many of the interesting problems in computational science have already been solved. Now, yes, we know there are certain problems that require exascale class performance, which doesn't exist, but those, quite honestly, are relatively few. So how can data science or deep learning be applied to high-performance computing? It's in that training pipeline and taking those large data sets that are being created by your computational science and finding new scientific discoveries in that data through deep neural networks. But rest assured, we didn't forget about computational science when we built the Pascal GPU. The Pascal P100, which today is our most powerful GPU, it starts off, of course, with blazing fast, double precision performance. We know that for all of our careers, for any computer that you buy for years to come, double precision performance will be important. So at 5 teraflops of FP64, this is the fastest processor in the world. It takes us a lot of transistors to do that. 15.3 billion transistors. That's more than double your typical CPU, and more than double certainly in performance. But we didn't stop there. Of course, it has great single precision performance, but more importantly for deep learning, half precision is actually enough for many types of deep neural networks. And so our engineers, our hardware engineers, figured out to take the same floating point unit and in the same amount of time have it do 1 double precision, 2 single precision, or 4 half precision. And this is actually really opening up a new bag of tools, a new technique for traditional HPC codes. In fact, computational fluid dynamics has often been very double precision focused. And we're working with the Technical University of Berlin and a large German automotive company that has taken some of their CFD models and running them on DGX1 in half precision and getting very good results. Now again, I'm not trying to say that half precision or single precision will replace double precision, but it's very interesting now that this capability is here to see traditional high-performance computing programmers look and see how they can adapt FP16 to their systems. The second big feature that was added that's very useful for HPC is NVLink. We found that over the last 10 years, over 400 applications in the scientific domain have been ported to the GPU. And typically, a programmer starts and does a single GPU port. And then once they get that running, then they say, well, let's now port the application to multiple GPUs. And as soon as you do that, the traditional PCIe bus, which has a maximum throughput of about 16 gigabytes a second, starts becoming a bottleneck. If you have a CPU doing a few hundred gigaflops of floating point, PCIe bus is just fine to communicate. But again, once you put 4 or 8 GPUs at 5 teraflops each, PCIe basically breaks down. And so NVLink is our own high-speed bus that we developed. It's integrated into the GPU and provides a combined bandwidth of up to 650 gigabytes a second. Now, you don't have to be someone expert in communication patterns to know that 750 versus 16 is going to give you much better performance. Let's go ahead and look at what other technologies are actually in the P100. For many years, we've used a technology called graphics memory, or GDDR, on GPUs. And if you're ever ambitious and you take apart that plastic casing around a GPU, you'll see a little printed circuit board, and it has a GPU in it, and then it has memory DIMMs on that printed circuit board. And of course, the printed circuit board has copper wires, and you basically have a limitation both in bandwidth and in power, the power you can feed into the GPU and the signals you can drive out of that. From physical space, on effect, pins in the GPU going to that printed circuit board, as well as the power that you can feed in. So we worked with our silicon suppliers and developed a totally new technology for assembling the GPU and the memory. It's called chip on wafer on substrate. And it starts with a new type of memory called HBM2. HBM2 is a so-called type of 3D memory. Then rather than being a memory DIMM on a printed circuit board, it stacks multiple memory DIMMs, 4 to 8 memory DIMMs on top of each other, and runs little silicon wires between the memory DIMMs. But now that you have that stack of high bandwidth memory, and high bandwidth because you have the silicon wires versus copper pins coming out, how do you connect it to the GPU? Well, the chip on wafer on substrate process takes the GPU and those stacks of silicon DIMMs and mounts that not on a printed circuit board, but on another piece of silicon. So now instead of having about 100, order of 100 wires going from the CPU to the DIMMs, you have on the order of 1,000 silicon wires going through, and at a much lower power per bit. 1/4 the power per bit to drive that silicon wire versus a copper wire. So that gives us 720 gigabytes per second of memory bandwidth per each GPU. And finally, to support a software concept called unified memory, with Pascal, we introduced hardware support for that called the page migration engine. Historically, what you had to do with the GPU was you had to move all your data over to the GPU before you started the program. And with CUDA 6, 2 years ago, we actually got rid of that limitation in software. But the runtime still had to move the data over before it started the GPU kernel or subroutine from running. With the Tesla P100, the first GPU to support the page migration engine, basically it creates a single virtual address space that spans not only all the GPUs and their memory in the system, but reaches out and includes all of the CPU memory on the server. So you can start running your program. You have a virtual memory space across the entire server. And if the GPU tries to access a memory location that exists on another GPU or out in the CPU memory, the page migration engine will automatically move that page of data over to that GPU's memory. So all of these things together work together to provide some amazing performance improvements. Now, the P100 was announced in April and started shipping in August of this year. So it's been shipping less than 6 months. And here's already a number of different applications. I did throw in a data science or deep learning application, AlexNet, but the rest of these are traditional HPC applications. And you can see the performance here comparing 2 K80s, or previous double precision GPU, with 2 P100s, 4 P100s, and 8 P100s to show you the scalability. Now again, some of the codes like VASP. VASP was only recently ported to GPUs, so it's multi-GPU scalability, at least above 2 GPUs, still needs some work, and so we're continuing to work with VASP. But again, excellent performance across the board, not only compared to the CPU baseline, but compared to K80. Now let's look at what happens when you put multiple GPUs together in a single server. This really takes advantage of strong scaling. And it's interestingly, very different approach than what some of our CPU competitors take with so-called weak scaling of small single socket nodes. So again, using the deep learning benchmark Caffe, you can go all the way out to 64 servers and still be getting only about half of the performance of a single server with 8 P100s. And again, on VASP performance, again, looking at scaling, VASP performance really levels out, and with 32 nodes on a CPU, you're still not getting the same performance that you get with 8 GPUs in a single server. And think about all of that other complexity of managing 32 or 64 servers times however many you have. The cables, the networking, the OS or software licenses, the system management, the loading the software, managing the software. So again, we believe there's a number of advantages of building these so-called strong nodes. Scaling within the node is always going to be easier before you try to scale outside of the node. Now, a lot of times people say, well, yes, that's true. A GPU server is faster, but a GPU server costs more money. Well, that doesn't take an HPC expert to figure out, right? If you have a server with no GPUs and you add GPUs to it, it's going to cost more money than the server without GPUs. But again, it's not the question of what does the server cost. It's a question of what does your data center, what does your HPC cluster cost? That's not only the cost of the servers, but everything else around it. And in fact, these numbers come from Microsoft's Azure HPC nodes. So on Azure, their HPC nodes, only 39% of the cost comes from the computers themselves for their HPC instances. The rest are the racks, the networking, the infrastructure in the system. Now let's take a look. And again, these are numbers from running on Azure's data center, Microsoft Azure's data center, using comparing one rack of GPU servers, 20 servers with 8 GPUs each. That was not on Azure because they're not running P100s yet. You have to ask them when they will roll out P100s, but we expect soon. To run VASP, you would need 7 racks of servers. That'd be 960 CPUs. And again, going back to something that's very important in India, as well as, quite honestly, around the world, is the power. 32 kilowatts for 1 rack of GPUs, 260 kilowatts for 7 racks of CPUs. And if you believe that when you build an HPC data center, you will have people that want to use that for deep learning applications, there the differences are even more dynamic. So putting it together, right, with GPU servers, not only is the total cost of that rack of servers less, size of the circle is smaller, but because you have fewer components, more of your budget is actually going to the compute versus all of the other infrastructure. By the way, NVIDIA doesn't make cables, so we don't make any money selling you cables. So it's to our advantage to make that other part smaller. So here's our end-to-end family today. We've been very busy. Last time I was in India was actually for IHPC India, which was just under 12 months ago, December last year. And none of these products were available. None of these products were announced then. So we introduced the Tesla P100. For inferencing, we introduced the P40 and the P4. We introduced a brand new form factor. So the Tesla P100 with NVLink. NVLink, remember, is a separate interconnect, so it made sense that that PCIe form factor with a PCIe connector doesn't have any ability to support NVLink. So we built a new high-density connector. We have a number of different server vendors besides NVIDIA are now using this new high-density form factor. And of course, we realize many of you don't want to buy new servers. The Tesla P100 for PCIe gives you all of the benefits of Tesla in your existing servers. Now, you have to go back and talk to your server manufacturer and ask them, well, if I'm running K80, will it run P100, right? It may be a BIOS change. There may be other limitations. But again, I will tell you, in my data center that I run, one of my data centers, I have a bunch of Supermicro servers and HP servers and Dell servers and other servers. And so far, every system that I put P100 in has worked. Doesn't mean that it's necessarily supported by the server vendor, but fairly good compatibility. And finally, our own deep learning supercomputer, DGX-1. Interestingly, DGX-1 was designed for deep learning. It's a full solution that includes not only the hardware, but NVIDIA-optimized versions of all the popular deep learning frameworks. But we've had a number of HPC customers that simply because this was the first server available with P100, that they've bought DGX-1s for HPC workloads. Turns out to be a great box, and I'll give you some numbers to talk about exactly how great it was. So again, we really do focus on having an end-to-end AI and HPC computing platform, working on the software, servers of all types, as well as the GPUs. But let's talk about some examples of some customers. I promise to share with you some things that traditional HPC customers are doing with deep learning. So NASA, NASA, the US Space Agency, has one of the world's largest archives of satellite imagery, right? And of course, today, there's a tremendous amount of interest of going in and measuring the impact of or carbon in the atmosphere, right? And I can pull up on my cell phone an app from any US embassy in the world and many other locations and see all the different statistics of how many particles are in the air, what's the carbon measurements in the air. But 5 years ago, 10 years ago, 20 years ago, those didn't exist, but there's satellite images from that space. So NASA took satellite images from different areas today and trained it using the carbon measurements from today, and then trained the system using GPU deep learning to look back at these 10, 20-year-old images and actually estimate and predict what the changes to the carbon in the atmosphere were based simply on the image data. A number of very other interesting examples. And like I said, I don't see many HPC centers today that aren't looking at that. Medical imaging and all sorts of other medical imaging workloads. And really every single industry is looking at AI and HPC types of applications today. IBM has a very interesting server that they announced. They liked NVLink so much when we told them about it that they use NVLink not only to connect the GPUs, but they built NVLink into their Power 8 CPU. So this server started also shipping in about the August timeframe. It has been very, very popular with customers. Finally, Microsoft. Microsoft has done some great work in the cloud and having one of the early HPC-focused instances using CPUs only. And now they've added to Azure Cloud new instances using GPUs. And in fact, we've seen all of the major cloud providers introduce new GPU offerings into their clouds. In one final slide, just to remind everyone, what we actually did, we were building up our own deep learning cluster, not for HPC, but for deep learning, using DGX-1. This is what our software developers, working on the NVIDIA self-driving car software, working on about 30 other deep learning projects at NVIDIA, this is what they use day to day. And my team said, we're going to build that, and said, okay, let's go ahead and take it for a day and run top 500 on it. Let's see what sort of performance we'd get. Now today, there are no systems with 124 servers on the top 500 list, CPU-only servers. We were actually able to get number 28 on the top 500 list with 124 servers. With 36 servers, we got 1 petaflop, which would have also been on the top 500 list. Think of that. Think of what it takes today to get on the top 500 list. 400 or 500 servers, the complexity of doing that. 36 of these servers gives you 1 petaflop. Still will be on the top 500 list for a while. And with 124 servers was 4.9 petaflops. More importantly, was on the green 500 list. Number 1 on the green 500 list. Almost 10 gigaflops per watt, 9.5 gigaflops per watt. The closest next to that is a special purpose processor out of Japan that there is virtually one of in the world, and it is at 6 gigaflops per watt. Xeon Phi, Intel's best HPC product, that gives you about 5 gigaflops per watt, and most Broadwell clusters are about 1/4 is energy efficient. So if you have a limited energy footprint, DGX1 is not only great for deep learning, but absolutely the most energy efficient HPC platform. So again, there's a lot of NVIDIA people out on in the show floor here, and we'd be happy to answer any questions outside. So thank you very much.
Thank you very much. Any questions? Yes. I'll have to step back. I cannot. Yes, please.
Hello.
Gentleman at the back. Yeah, please.
Yeah. This is deep learning is a half precision, right, sir?
Deep learning can run at any precision. Many deep neural network models run very well on half precision. Not all. It's really dependent on the data type and the type and size of your network.
Like when we like learning when it's happening in the deep learning, if data is in precision based, so how this deep learning is take the decision based on the precision number of the system in the data set? If I consider like P100 as in high performance computing for scientific tools evaluation, how I can assure that this P100 can be like useful for me to develop scientific exploration tools?
Well, again, from the FP64 versus half precision, that's built into the hardware, right? So again, that's the capability. As to when do you use FP16 for deep learning, again, that's what the data scientist does typically.
It can be used for as a standalone server where it can be computed as a supercomputer, not for to make a supercomputing in precision format. That it cannot be the advantage. And like what I found from the you were saying, it is for half precision format where it is taken up, right? For P100 processors or deep learning processors and the tools.
So the tools, CUDA 8 gives you the ability to use all of the different precision formats.
So in the software side, I have to tune that in this.
Yeah.
Yes, your software needs to be aware of what precision. It's no different than on a CPU, right? You need to tell your CPU if you want to use a double or a single precision.
Yeah. Somebody at the back standing would like to ask a question, then this gentleman.
So it was nice when you talk about the architecture. So if you look back over the last 3-4 years, a great change in AI was actually facilitated because algorithms actually went in a biologically inspired way, especially in deep learning. So you could possibly see in the Gartner 2017 hype cycle, they have included neuromorphic computing. So how would you see NVIDIA moving? Because there is huge change in the way computing is done algorithmically by the inclusion of deep learning and then methodology. But the architecture has improved a lot, but the basic technology and the stack still remains pretty much same, right? I mean, of course, NVLink and all that has changed, but do you see some drastic change in architecture from what you have now or what you've been having for the last decade to something close to the neuromorphic computing arena or something really drastic and different?
So GPU computing has been fairly a similar architecture for 10 years. And that's exactly correct. Now, I'm not sure we can see 10 years into the future. We look at all of the other architectures out there, from neuromorphic computing, spiking neural networks, the use of FPGAs, and it's very interesting. Some companies are doing one of each, right? NVIDIA is very focused. We're focused on our GPU computing architecture. We have been for 10 years since we introduced CUDA, and certainly everything that we see, I'll say, out to 5 years in the future, which is sort of our planning cycle. We're very focused on that. And again, if something more interesting comes out there, we'll certainly consider that as we get there. But we don't see any, we're remaining very steadfast on our architecture today. And in fact, we don't think, look, going off and buying 5 different architectures and combining them into one company, that doesn't make an architecture. That makes 5 different things, but in under one roof. So,
Yeah, one last question. Yes.
Actually, I have 2. Sorry. I've seen page migration in one of your slides. Now, does it really help improve performance, or is it something that helps improve programming? I mean, or what do you think? Does it help improve performance?
So certainly both, right? One is unified memory was really that big step to enabling ease of use in programming. The page migration engine is just providing a performance improvement, hardware-based support for that. So if you say, does the page migration engine provide performance improvements over programmer hand tuning and hand interleaving, the weaving of memory? You know, a really good programmer can probably get similar performance. And in fact, all of that effort that programmers have done over the last 10 years with CUDA remains to be valid, right? The page migration engine is just another way to do that.
Okay. The other one is Dr. Steve Parker actually spoke about 5 miracles. I couldn't ask him any questions that time, but I noted down a couple of miracles, one being P100, NVLink, and CUDNN, but I didn't quite get the other 2. So I'm not sure if page migration was part of it, or sorry, it's a difficult question.
Yeah, no. The 5 miracles of Pascal that we talk about is first is the 16 nanometer FinFET transistor. We use that. You know, now that wasn't developed by us, right? That was our fab, but that's one of the 5. The Pascal architecture. So that includes a number of things such as the FP16 support. The HBM memory is the 3rd. The NVLink is the 4th. And then all of the software features where the page migration engine would be included in that is the 5th. So those are the 5.
Thank you very much.